Hello! The topic of this lecture is part of speech tagging, and the goal is to answer the following questions. What are lexical categories and how are they used in natural language processing? How can we automatically tag each word of text with its word class? Words can be grouped into classes such as nouns, verbs, adjectives, or adverbs. These classes are known as lexical categories or parts of speech, and the process of automatically assigning parts of speech to words in text is called part of speech tagging, pause tagging, or just tagging. And these tags reveal a lot about word and its neighbors. Knowing whether a word is a noun or a verb tells us about likely neighboring words. For example, nouns are preceded by determiners or adjectives, verbs by nouns. The tags give an idea about syntactic structure. For example, nouns are generally part of noun phrases, hence helping in text pausing. The pausing is the process of determining the syntactic structure of text by analyzing its constituent words based on an underlying grammar. Parts of speech are useful features for labeling named entities like people or organizations in information extraction or for co-reference resolution. A word's parts of speech can even play a role in speech recognition or synthesis. To summarize, automatic tagging is an important step in the NLP pipeline and is useful in a variety of situations, including predicting the behavior of previously unseen words, analyzing word usage in corpora, and text-to-speech systems. Part of speech tagging is the process of classifying words into their parts of speech, word classes or lexical categories, and labeling them accordingly. Tagset is a collection of tags used for a particular task. But how do we decide what category a word belongs to in the first place? In general, linguists use morphological, syntactic, and semantic clues to determine the category of a word. The internal structure of a word may give useful clues as to the word's category. For example, ness is a suffix that combines with an adjective to produce a noun. For example, happy, happiness, ill, illness. So if we encounter a word that ends in ness, this is very likely to be a noun. Similarly, ment is a suffix that combines with some verbs to produce a noun. For example, govern, government, establish, establishment. English verbs can also be morphologically complex. For instance, the present participle of a verb ends in ing and expresses the idea of ongoing incomplete action. For example, falling or eating. The ing suffix also appears on nouns derived from verbs. For example, the falling of the leaves, which is also known as the gerund. Another source of information is the typical context in which a word can occur. For example, assume that we have already determined the category of nouns. Then we might say that a syntactic criterion for an adjective in English is that it can occur immediately before a noun or immediately following the words be or very. According to these tests, near should be categorized as an adjective. For example, the near window or the end is very near. The meaning of a word is a useful clue as to its lexical category. For example, the best known definition of a noun is semantic, the name of a person, place, or thing. Within modern linguistics, semantic criteria for word classes are treated with suspicion, mainly because they are hard to formalize. Nevertheless, semantic criteria underpin many of our intuitions about word classes and enable us to make a good guess about the categorization of words in languages that we are unfamiliar with. For example, if all we know about the Dutch word verjaardag is that it means the same as the English word birthday, then we can guess that verjaardag is a noun in Dutch. However, some care is needed. Although we might translate zij is vandaag jarig as it's her birthday today, the word jarig is in fact an adjective in Dutch and has no exact equivalent in English. All languages acquire new lexical items. A list of words recently added to the Oxford Dictionary of English includes cyberslacker, fatouche, blamestorm, SARS, Cantopop, Bapkis, Nutties, Muggle, and Robada. Notice that all these new words are nouns, and this is reflected in calling nouns as an open class. By contrast, prepositions are regarded as a closed class. That is, there is a limited set of words belonging to the class, for example, above, along, at, below, beside, between, during, for, from, in, near, on, outside, over, past, through, towards, under, up with, and so on. And membership of the set only changes very gradually over time. Common tagsets often capture some morphosyntactic information. That is information about the kind of morphological markings that words receive by virtue of their syntactic role. Consider, for example, the selection of distinct grammatical forms of the word go, illustrated in the following sentences. Go away. He sometimes goes to the cafe. All the cakes have gone. We went on the excursion. Each of these forms, go, goes, gone, and went, is morphologically distinct from the others. Consider the form goes. This occurs in a restricted set of grammatical contexts and requires a third-person singular subject. Thus, the following sentences are ungrammatical. They sometimes goes to the cafe. I sometimes goes to the cafe. By contrast, gone is the past participle form. It is required after have and cannot be replaced in this context by goes, and cannot occur as the main verb of a clause. All the cakes have goes. He's sometimes gone to the cafe. We can easily imagine a tag set in which the four distinct grammatical forms just discussed were all tagged as VB for verbs. Although this would be adequate for some purposes, a more fine-grained tag set provides useful information about these forms that can help other processors that try to detect patterns in tag sequences. The Brown tag set captures these distinctions as shown in this table. So some morphosyntactic distinctions in the Brown tag set are, for example, for the base form of the verb is VB, but the third person singular for present is tagged as VBZ. Then the past participle is tagged as VBN, the gerund VBG, and the simple past VBD, and so on. This fine-grained tagging of verbs means that an automatic tagger that uses this tag set is effectively carrying out a limited amount of morphological analysis. Most part-of-speech taggers make use of some basic categories, such as noun, verb, adjective, and preposition. However, taggers differ both in how finely they divide words into categories and in how they define their categories. For example, is might be tagged simply as a verb in one tag set, but as a distinct form of the lexeme be in another tag set, as for example in the Brown corpus. This variation in tag sets is unavoidable since part-of-speech tags are used in different ways for different tasks. In other words, there is no right way to assign tags, only more or less useful ways depending on one's goals. Tagged corpora use many different conventions for tagging words. To help us get started, we'll be looking at a simplified tag set shown here and is known as universal part-of-speech tag set. Nouns generally refer to people, places, things, or concepts. For example, book or intelligence. Nouns can appear after determiners and adjectives and can be the subject or object of the verb. Verbs are words that describe events and actions, for example, fall or eat. In the context of a sentence, verbs typically express a relation involving the reference of one or more noun phrases. Two other important word classes are adjectives and adverbs. Adjectives describe nouns and can be used as modifiers. For example, large in the large pizza, or in predicates, the pizza is large. English adjectives can have internal structure. For example, fall plus ing in the falling stocks. Adverbs modify verbs to express the time, manner, place, or direction of the event described by the verb. For example, quickly in the stocks fell quickly. Adverbs may also modify adjectives. For example, really in Mary's teacher was really nice. English has several categories of closed class words, in addition to prepositions, such as articles, also often called determiners, for example, the or a, modals, for example, should or may, and personal pronouns, for example, she or they. Each dictionary and grammar classifies these words differently. The problem of part-of-speech tagging, that is, categorizing words from a sentence into lexical categories, will be solved using hidden Markov model. So we start with an input sequence, that is x1 up to xn, where xi is the ith word in a sequence or input sentence. We also have a tag sequence y1 up to yn, where yi is the ith tag in a sequence. And then we'll use HMM, hidden Markov model, to define the joint probability of these two sequences for any sentence x1 up to xn and any tag sequence y1 up to yn of the same length. And then by calculating argmax of this joint probability, we'll find the most likely tag sequence for x. In order to find the tag sequence which maximizes the joint probability of an input sentence and tag sequence, we'll use Trigram hidden Markov model. So for any sequence x1 up to xn, where xi is an element from our vocabulary, and any tag sequence y1 up to yn plus 1, where these y's are elements from the tag set, where yn plus 1 element, the last element of the sequence, is the stop symbol, the joint probability of the sentence and tag sequence is given with the following equation. So we have the product of these q and e terms. Q term is a conditional probability of a tag given to previous tag, and emission element e is the probability of a word given a tag. And we also define the initial conditions, so these first two elements of the input sequence equal to the star symbol. And basically we have the parameters of our model, Q's and E's. So a Q, conditional probability of S given U and V, for any S from the joint set of this set S in union with stop symbol, and UV elements from the union of S set and star symbol, and also this emission parameter is a probability of X given S for any S from S and X from V. So let's see an example. So let's say that we have a sequence with 3 words that is equal to this particular sequence, a willow wiggles, and we also have the 4-element tag sequence, D for determiner, N for noun, V for the verb, and the last is the stop symbol. So this is a special tag that terminates the sequence. So in order to calculate the joint probability of these 3 words and these 4 tag elements, we have to multiply these product terms, Q and E terms. So let's start from the beginning. So first is this Q term, the conditional probability of a determiner given 2 stars. So let's recall that our tag sequence starts with these 2 stars as defined here. So this star is a special padding symbol. Then we have the Q term, the probability of the noun given star and determiner. Then times this Q term, the probability of a verb given determiner and noun. And the last element is the sequence, the stop symbol. So the probability of the stop symbol given previously noun and a verb. And then we also multiply these E emission symbols, the observed words probabilities. So first we have the probability of the word A given the determiner as a tag, then we have the probability of a word wiggle given n as the tag, and times the probability of a word wiggles given the v as a tag. In order to calculate conditional probabilities from the previous slide, we can use smoothed estimations such as linear interpolation, as shown here. So, for example, if we want to calculate the conditional probability of a verb given determiner and a noun, we can use the linear combination of the maximum likelihood estimates of the trigram, bigram, and unigram models. These lambda parameters, these three lambdas, sum up to 1, and each of them is greater or equal to 0. And the calculation goes as follows. So lambda 1 is multiplied with the maximum likelihood estimate for the trigram. So this estimate is basically the ratio of the number of trigrams and bigrams. Then lambda 2 is multiplied with the maximum likelihood estimate for the bigram model, so it is the ratio of the count of bigrams and unigrams. And lambda 3 is multiplied with the maximum likelihood estimate of unigram model, so the ratio of the number of verbs divided by the total number of tags occurring in our tag set. And then here we can see an example of how to calculate the emission terms. Here we have the example of how to calculate the probability of a word wiggles conditioned on a verb tag. So here we use the bigram model. So we divide the number of bigrams, that is the verb and wiggles, with the number of verbs in our training data set. Since the number of possible tag sequences grows exponentially with the length size of the input sequence n, this problem of calculating joint probability of an input sequence and tag sequence is calculated by using the Viterbi algorithm. The Viterbi algorithm takes an input of x1 up to xn and calculates argmax. This argmax is taken over all sequences y1 up to yn plus 1, such that each yi is an element from the tag set, and the last element in the sequence, that is yn plus 1, equals to the stop symbol. And this joint probability of an input sequence and tag sequence equals to the product of q and e terms, as we previously explained. So we have n plus 1 q term, which is basically the conditional probability of a tag given to previous tags. And then we also have these n emission terms, where each emission term is a probability of a word conditioned on a tag. And each tag sequence starts with these two star symbols. The Viterbi algorithm defines n to be the length of the sequence, and then it defines sk for case equal -1, 0, 1 up to n to be the set of possible tags at position k. So we have set s-1 equals to the set s0, which is basically the set with only star element in it. And then for the rest of the case, a case from 1 up to n, we have sk equals s, which is set of our tags. And then the Viterbi algorithm defines this function r, which takes the sequence of these y elements, so y from -1 up to k, and it calculates the product of these kq terms and ke terms. So, as we said before, these q terms are basically the conditional probabilities of a tag given to previous tags, and the emission parameters are calculated as the probability of a word given a tag. And next, for the Viterbi, we define a dynamic programming table such that we have this pi function. So pi with the input of ku and v is the maximum probability of a tag sequence ending in tags u and v at position k, which we formally define with the following expression. The maximum probability of a tag sequence ending at tags u and v at position k can also be calculated recursively. So here we have a recursive definition, which we start with a base case of the pi of 0 and 2 stars equals 1, which basically refers to the fact that each tag sequence starts with 2 star symbols. So for any k in this set, 1 up to n, and for any u in sk minus 1, and v in sk, the following recursive definition holds. This definition is recursive because this definition makes use of this term, pi of k minus 1, w and u, which is computed for shorter sequences. This definition is the key to our dynamic programming algorithm. How do we justify this recurrence? So recall that pi of k, u, and v is the highest probability for any sequence, y minus 1 up to y, k, ending in the bigram u, v. Any such sequence must have y k minus 2 equals w for some state w. The highest probability for any sequence of length k minus 1 ending in the bigram wu is pi of k minus 1 w and u. Hence the highest probability for any sequence of length k ending in the trigram w, u and v must be equal to this. So the pi of k minus 1 w and u times the q parameter of u given w and u times the emission e parameter of xk given v. Here we have the pseudocode for the basic Viterbi algorithm that puts all the previously explained ideas together. So the algorithm takes a sentence x1 up to xn and the parameters q's and e's. So this q is a conditional probability of a tag s given tags u and v, and the emission parameter is a conditional probability of a word x given the tag s. The algorithm returns the maximum probability of a sequence that ends with tags u and v at position n. Also, the algorithm uses some definitions, so the k is the set of possible tags where we emphasize that each tag sequence starts with these 2 star symbols. Also, as the algorithm uses the recursion, we have to set this base case to begin with, so we initialize the function pi of 0 and 2 stars to 1. So the rest of the algorithm was previously explained, so we can only tackle the problem of calculating the complexity of the algorithm. So here we can see that the algorithm goes linearly through the sequence of words. So we have n times. Then also another step when we choose u and v among k elements from the tag set. So basically we have the k times k combinations here, and also within this step of calculating pi we also have to choose between k cases. So when we put all this together we can conclude that the complexity of this algorithm is basically n times k to the power of 3, where I mean the number of elements here in the set k. So this is significantly reduced when we compare this complexity to the brute force search algorithm, which would be k, the number of tags in a set k to the power of n. The algorithm we have just described takes a sequence x1 up to xn as input and returns the maximum probability as its output. However, we would really like an algorithm that returns the highest probability sequence, that is the algorithm that returns argmax. So we have here the pseudocode of the Viterbi algorithm with back pointers, which is a slightly modified algorithm that achieves this goal. So the key step is to store back pointer values, BP of k, u, and v at each step. So the modification, if we compare this pseudocode with the previous slide, the modification is in this line of the code. So these back pointer values record the previous state W, which leads to the highest scoring sequence ending in UV at position K. And the use of back pointers such as this is very common in dynamic programming methods. At the end of the algorithm, we unravel the back pointers to find the highest probability sequence and then return this sequence. The algorithm again runs in the same complexity, so it is O of n times k to the power of 3. So let's see an example. Say we have a training set consisting of 2 tagged sentences. So the first sentence is the can is in the shed. So it is tagged as follows. So the is a determiner, can is a noun, is a verb, in is a preposition, D is a determiner, shed is a noun. And the second sentence is the dog can see the cat. So it is tagged as follows. So there is a determiner, dog is a noun, can is a verb, see also a verb, the determiner, and cat is a noun. And then we train a bigram tagger of this form, so to calculate the joint probability of a sentence and the corresponding tagged sequence, we need to multiply these Q and E terms. So we have n plus 1 Q terms, the probability of a tag given a previous tag, and the probability of a word given a tag. So we calculate these Q and E parameters by using simple maximum likelihood estimates. And if we then use the Viterbi algorithm to find the maximum probability tag sequence for each of the training sentences, our task is to show that the tagger tags both sentences correctly. So the only word which is seen with more than one tag is can. So in this first sentence, can is a noun, and in the second sentence, can is a verb. Hence, can is the only word such that E parameter, E of a word given a tag, is greater than 0 for more than one tag, Y. Now, if we consider the two incorrect taggings, so if we say that falsely this first can was tagged as a verb, and then the second can was tagged as a noun, then we can see that both have probability 0 under the maximum likelihood model. The first sentence has the tag bigram determiner verb, which is never seen in the training corpus and hence has an associated parameter Q of a verb given a determiner 0, resulting in the entire tagged sentence having probability 0. And the second sentence has a tag bigram noun noun that is also never seen and hence has the probability 0. It is easy to verify that the two correct tag sequences both have probability greater than 0. The problem is to come up with a training set such that when we train a bigram tagger using maximum likelihood estimates, the resulting model makes at least one mistake on the training set. So let's consider a training set consisting of the single tagged sequence as shown here. So we have these 6 does and each is labeled with determiner except for this second that is labeled as a noun. So in this case we have the maximum likelihood estimates as follows. So the probability of the given a determiner equals the probability of the given noun, which is 1. And for the Q terms, we have the probability of a noun given determiner as 1/5. The probability of a determiner given determiner, we have 3/5. And the probability of the stop symbol given determiner, we have 1/5. And it can be verified that the most likely tag sequence for these 6 does is actually the 6 determiners and the stop symbol.